In the previous session, we have seen the closest mathematical statement of the second law of thermodynamics, which could be broken up into two parts. One part applicable for reversible processes only, known as the closest theorem, and the other part applicable for the irreversible process, which we called as the closest inequality. Now we will discuss each of these processes one by one. In this session we will be discussing the reversible part of the second law. So from our previous discussions, you are very familiar that in order to denote any thermodynamic processes, we can use the indicator diagram. Usually a PV diagram is used as the most common indicator diagram in order to denote hydrostatic systems. Now, if you generalize the concept of indicator diagram for all type of hydrostatic systems, say a magnetic system or an electric system or something involving surface tension, etc., etc., we will call such generalized indicator diagram by the name a Vogt diagram. So this is a Vogt diagram. What is a Vogt diagram? Try to understand. Vogt diagram is a generalization of the concept of an indicator diagram or a PV diagram. So far we have been using pressure volume diagrams, and we call it in engineering terms as indicator diagram. A generalized concept for this PV diagram is what is known as the Vogt diagram. Let's see what are the axes used in such a diagram. You can see on the y-axis we are taking quantities which are labeled as generalized force. Quantities which are taken as generalized force represented as y. You say y because it's taken along the y-axis, that's all. Okay, and along the x-axis we take quantities which are generally termed as generalized displacement. So you can just see on x-axis, if you forget about the word generalized, x-axis has got displacement and y-axis has got some quantity which is behaves like force. So what is force times displacement in general mechanics? So you know that force multiplied by displacement is nothing but giving you work. Dimensionally it will be giving you work, right? So that is why such diagrams whose axes are generalized forces and generalized displacements commonly known by the name Vogt diagram. So you can just verify with this one with specific quantities. For example, in place of this generalized force and generalized displacement, we have been using pressure and volume, right? Okay, pressure and volume. So pressure was in place of generalized force and volume was in the place of generalized displacement. So you can see that when you multiply pressure into volume, you can just check it by yourself. You do it dimensionally, you will be getting the dimensional formula of pressure into volume is nothing but work done. Dimensional formula of work you will be getting. Okay. Of course, you remember that we calculated the work done during a thermodynamic process by calculating the area under the PV diagram. Okay, that itself says that okay, the PV diagram is nothing but a Vogt diagram. So that is a specific example that we are familiar with. Now we try to generalize it. See, we have used two terms here. One is generalized force and other one is what? Generalized displacement. What is meant by generalized force? Any physical quantity that behaves like the force. Okay, so force like quantities, I can say. Force like quantities in thermodynamics is usually termed as generalized force. ഓക്കെ, നമ്മളതിനൊന്നൊരു സാമാന്യവൽക്കരിക്കുക മാത്രമേ ചെയ്യുന്നത് ഇവിടെ. ഇപ്പോൾ ഇക്വേഷൻസിലൊക്കെ വർക്ക് ഡയമെൻഷനായിട്ട് വരുന്ന ഇക്വേഷൻസ് എഴുതുകയാണെങ്കിൽ നിങ്ങൾക്ക് കാണാൻ പറ്റും, നമ്മൾ കണ്ടുവിടെ പ്രഷർ ഇൻറ്റു വോളിയം ഈസ് വർക്ക് എന്ന് കണ്ടു. അതുപോലെ തന്നെ നിങ്ങൾക്ക് കാണാൻ പറ്റും, നിങ്ങൾ സർഫസ് ടെൻഷൻ, ഉദാഹരണത്തിന് സർഫസ് ടെൻഷൻ, നമ്മൾ സർഫസ് ടെൻഷനെ ഈ ഒരു സിമ്പിൾ വെച്ചിട്ടാണ് മുൻപ് തെർമോഡൈനാമിക്സിൽ സൂചിപ്പിച്ചത്, സ്ക്രിപ്റ്റ് ലെറ്റർ എഫ്. സർഫസ് ടെൻഷൻ ഒരു ഇൻറ്റൻസീവ് വേരിയബിളാണ് നമ്മൾ കണ്ടിരുന്നു അല്ലേ. അതുപോലെ മറ്റ് we used this symbol for tension, not surface tension. Tension in strings, right? So this is tension in strings. Surface tension we denoted by gamma, is not thermodynamics. Okay, we are using surface tension by gamma. Then maybe we used quantities like EMF, is not. All these quantities were intensive variables. So these are all intensive variables, and we have seen that the pressure also is also an intensive variable. Okay, so intensive variable pressure, you can add pressure also with this one, and we had quantities, extensive variables corresponding to each of these intensive variables in thermodynamics. For example, corresponding to tension we had length, right? So corresponding to tension we had a length of the string. Corresponding to the surface tension we had the area of the film. Okay, corresponding to the EMF we had the charge. Okay, corresponding to the pressure we had that volume. Okay, so likewise you can go for magnetic systems and so on and so forth. So these are all extensive variables. Okay, and what is the speciality of this set of variables? You multiply one intensive variable with the corresponding extensive variable, you will be getting the dimension of work. So you can always represent these two quantities as the two axes of a indicator diagram, and then that indicator diagram will be generally known as work diagram. So I can say that this force, okay, surface tension, or sort of tensions, the surface tension, EMF, etc., are behaving like force. And these quantities, the length, the area, the charge, the volume, etc., are behaving, or they are performing the role of some displacement. So we call these quantities generally as generalized force and generalized displacement. And the criteria, as I have already mentioned, is that always multiplying generalized force with the generalized displacement should always be giving you the work done during the process. So that is why we call it as what? The work diagram. Hope that idea is clear. So it's only for our convenience that we categorize the quantities into two categories, right? Okay, so that's fine, I think. Now on the right side, having understood what is a work diagram, you can see the diagram given over here. So in the diagram here, just you see reversible process is represented in the diagram. So I in the diagram denotes the initial state of the system, and F in the diagram denotes the final state of the system. Okay, so if it's a PVT system, then it can be some generalized force will be the pressure here, generalized displacement will be the volume here. So there will be some PI, VI, TI here corresponding to I, and there will be some PF, VF, TF corresponding to the point F here. That's all. Okay, if it is string problem, then there will be a corresponding value of tension here, there will be a length here, and there will be a temperature here. In all the quantities, temperature will be one of the three thermodynamic variables, and there will be a final value for all those parameters here. So this is a general picture, that's all. Okay, now see, so the picture here, the process is represented by the curve IF. So it's a smooth curve, you can see that, of some shape. So this is the IF. So I'm just drawing it over the curve, you can see here. IF is a reversible process. You assume that it's a reversible process. Okay, going from I to F, you can just imagine like this. So what we are going to do, we are going to just break up this reversible process into some other series of process. Okay, so how we are doing, you can just see in the diagram here. You can see some dashed lines here. See, the dashed line is passing through I. So let me call this dashed line as IA, is it not? You can see this particular part, this dashed line. So that is going through I, the initial state of the system, and let me denote a part of the dashed line as IA, okay, where A is not defined so far. Similarly, you can see another dashed line here which passes through the final state. So this is the other dashed line. So these two dashed lines represent, let them represent two adiabatic processes. Some adiabatic process that happens to be a point, okay, sharing the initial and final point. So let these dashed lines represent two adiabatic processes, right? Okay, now you can see there is another dashed line here. There is another dashed line here which is labeled as AB. This is labeled as AB. Okay, so it's a standardized line. So this is labeled as AB here. So this AB, let it be representing an isothermal process. So maybe you think that why do you name first IA and BF as adiabatic, and why do we say that this AB is isothermal? You know that in a PV diagram that the adiabatic curve will be always steeper than the corresponding isothermal curve, right? So you can see that an isotherm will be connecting to adiabats, right? So an isotherm can connect to adiabats because adiabats will be different adiabats will be at two different temperatures, right? And an isotherm, you can just see that this isotherm can connect, because the adiabats all along the adiabat the temperature can change, right? So isotherm can connect these two particular adiabats. That is what we have seen there. So this isothermal curve is just AB. Now the question is that where this AB will be drawn. Where do we draw this AB? So will you be drawing AB here, see that close to I like this, or will you be drawing AB here? So how do we decide that? That's a question. You cannot draw AB anywhere as you like. The condition that we have followed in drawing AB or fixing points A and B in this diagram is that this particular there is some area under the curve IF, is not? Can you just imagine the area under the curve IF? What will be the area under the curve IF? So let me just show it by some shading. So this is the area under the curve IF. And you know what is this area under the curve IF denoting? If it is work diagram, you know this area under the curve will be denoting the work done during the process in going from I to F, right? So IF is our original area. IF is our original curve, remember. IF is the original curve. And we are transforming this curve, or we are trying to redraw this curve in terms of an equivalent set of other curves. Okay, so in place of this IF curve, we are using I. See the points in the diagram. A, from I we come to A, then from A we come to B, I, A, B, and from B we will come to F. So I, A, B, F. We should be making this curve IF equivalent to IABF. IABF. How it can be done? That you select the points A and B in such a way that the area enclosed by the curve IF is equal to the area enclosed by the mix of curves IABF. So that is a condition. What is the condition here? Area under IF curve, which I have shaded by using green lines. That should be equal to area under a zigzag curve. Okay, what is a zigzag curve? I, A, try to follow that in the diagram. I, A, B, F. That is a zigzag curve, right? So in this particular condition, in order to satisfy this condition, or in a way in which it will be satisfying this particular condition, you have to draw AB. So whether you draw AB here, or you will draw AB here, or you draw AB here, it will depend upon whether or not this particular condition is satisfied. Okay, and it's quite easy actually if you think in a way. This is actually it's a type of geometrical construction. See, how can you ensure that these two areas are the same? So do one thing, like you just make sure that see, when you use this particular path in place of the actual IF path, actually aren't you getting this particular area, what I am shading now in red, reduced? This particular area will be reduced from the area of the curve. That is now above the graph, right? So this much area is lost when you redraw the graph like this, right? So whatever area is lost should be compensated. So in order to compensate that, you just try to get an area here. That's what is being done here. See, you are gaining this area here. Can't you see that? See, this red shaded area of the curve is lost, and in order to compensate for that red shaded area, we are just gaining this black or blue shaded area here. Okay, so that whatever is lost is gained here, so it is compensated. Okay, now you can see that if you increase if you are drawing AB here, it won't be satisfied. Why? You will be losing this much area, you will be losing large amount of area, and you will be gaining only very small amount of area, so that is not satisfied. Okay, so the reverse also you can think of. So there will be some particular points A and B on the two dotted lines adiabat in such a way that if you draw the two using an isothermal curve, the area under the curve IF will be compensated, okay, or to be equal to the area under the newly drawn zigzag curve IABF. So suppose that you have drawn such an area here. Hope the idea is clear to you, right? Now, why do we take such pain? Okay, why? What is our intention? We will see that. What is our intention? Okay, shortly. Okay. Now, so since these two areas are same, I can conclude that the work done. I'm writing W. W stands for work done during the process I to F. I to F is representing a thermodynamic process, right? I told you I am considering this is a reversible process because we are considering the reversible part of the second law of thermodynamics. So WIF will be in principle equal to WIABF, is it not? So whether the process is happening along the path I to F, a smooth path I to F, or it is happening along a zigzag path IABF, since the area under both the curves are equal, the work done, okay, during both of these processes should also be equal. So that is my argument. So this is first argument that we have. Okay, keep it there. Remember, this result we got from our construction, by construction I can say. This one is by our argumentative construction that we have followed here. By construction itself, this is ensured. Now, let's use the first law of thermodynamics. So by first law of thermodynamics, by first law, what is first law of thermodynamics? You know, it's a restatement of the law of conservation of energy. So how we have been writing? We have been writing it as some, in many ways we have written is delta U is equal to, for finite changes we have been writing it like this, no? Delta U, change in internal energy is caused due to two reasons. The heat exchange and the work done. So delta U is equal to Q plus W, or I can say that Q is equal to, okay, or can you write Q is equal to, what is that? Delta U minus W. Delta U minus W. And what is delta U? Can you write delta U as the difference between, you know, internal energy is a state function. So let's assume that the internal energy of the system at I state is Ui, and the internal energy of the system at the final state is UF. So what will be delta U? That should be equal to UF minus UI. UF minus UI, that is delta U. Being a state function, I can neglect the path. What will be the path? Whether it is IF or IABF, the delta U will remain the same. Minus, but W is path dependent, that we usually know, minus W. So I am writing minus W. That is the general way. So that is the first law of thermodynamics. Now let me apply the first law of thermodynamics for these two paths separately, okay, because work is involved, right? And heat also is, you know, their heat and work are in general path functions, you know. Heat and work are in general path function, but internal energy is a state function. That's what we have already defined, right? So let me say that I'm applying this equation, this particular equation for both the paths. So for I to F, for the path I to F, what should I write? Q on the LHS. Let me write clearly that it is the heat exchanged during I to F, QIF, either a gain or loss, that I don't care now. QIF is equal to, I can write clearly as UF minus UI, right, minus W. And this W, I should mention it is clearly WIF. I'm bound to do that, WIF, because work in general is path dependent. So we say that this is my second equation. right? Similarly, I should write this first law of thermodynamics for the other zigzag path that we have constructed, IABF. So what will be IABF? I can write QIABF. I am writing it like this. Once again, it is UF. There is no change about it. Minus UI minus, I should label this W also as WIABF, the corresponding value of the work there. So there is what? Equation number 3. Now, just have a look at equation number 1, 2 and 3. What you can conclude? What you can conclude? What you can conclude? See that this WIF is equal to WIABF, right? WIF is equal to WIABF. So this WIF and this WIABF have been made equal by our particular construction. Is right? So what is the conclusion out of the 2 and 3? So 1, 2 and 3 will give you a conclusion that, okay, both QIF and QIABF, they are equal to the same RHS, UF minus UI, UF minus UI. So what you be able to conclude that QIF, therefore QIF is equal to QIABF. QIF will be equal to QIABF. So that is a conclusion that we are going to get. So what does it mean? Just let's stop a bit and think about it. What does it mean? QIF equal to QIABF. So whether the thermodynamic process is proceeding along the smooth curve IF or it is proceeding along an equivalent zigzag curve made up of two adiabats and in an interconnecting isotherm, the heat exchange happening will be equal, or you will be able to always find out an equivalent zigzag path connecting the same two initial and final states corresponding to any reversible smooth process. Is it okay? That's our conclusion. See that, or finally you just stop and contemplate on what is the meaning of the equation that we are finally getting. That's something very important. QIF equal to QIABF if we are able to construct such a path. Now, not only that, let me call that this result as some 4. We have something more, right? Now, you look at the diagram here. See, in the path IABF, you know, we have got 3 subparts. You can divide IABF into 3 parts, which are IA, which is adiabatic, then AB, which is isothermal, and once again BF, which is adiabatic. But you know that there is no heat transfer during any adiabatic process. There won't be any heat transfer occurring during an adiabatic process. So what about the heat transfer contribution during IA part and BF part? That should be 0. So even though we have labeled this one as QIABF, the heat transfer during IA and BF is 0, and whatever heat that will be transferred into the system or out of the system will be happening during the isothermal part of the zigzag curve. Is it okay? I repeat, since there is no heat transfer in the 2 adiabatic processes IA and BF of the zigzag path, the heat that has entered or left the system will be during the isothermal part of the process, that is AB. So I need not now write QIABF. I can simply write this one as what? QAB. Okay, so that is the thing that we are going to do. So I can just conclude. We go to the next thing. It has been a bit more. So this is our conclusion, or this is our final equation. QIF is equal to QAB. QIF is equal to QAB. All right. Okay, so just have a clear look at the diagram, work diagram which I have reproduced here afresh. IF was our real thermodynamic path followed by a system undergoing reversible process. So I can either use I to F or F to I, you know, that is not going to make a difference because the process is reversible. And we have tried to replace the curve IF or the path IF with an equivalent set of paths, which is zigzag. IF is replaced with, this is equivalent to IABF. We have constructed the curve in such a way that, which consists of two adiabatic paths and one isothermal path. And you know, if we assume that Q is the heat that is transferred during the actual path IF, so QIF is the heat that is transferred during the actual or real path IF, we have concluded finally that this heat QIF will be equal to the heat that has got transferred during the isothermal part of the imagined path, QAB. Okay, so that is our conclusion here, right? So we'll come to our nominal conclusion here before we end up the session. If we are given, see that I have just used the statement that is in your textbook, and I think by the time you will be able to understand this one and appreciate what's the meaning. If we are given a reversible process in which the temperature may change in any manner, the temperature may be changing in any manner, so that is why it's a smooth curve. Okay, you can break up this curve into a number of patterns. So whatever way the temperature changes in the process, it's always, whatever be the curve, it's always possible to find a reversible zigzag path. So equivalent to any IF path, just drawing an equivalent reversible zigzag path between the same two states I and F, consisting of, there are some conditions, consisting of adiabatic process followed by an isothermal process, again followed by an adiabatic process. So adiabatic, then isothermal, again an adiabatic. Okay, such that what is the output or outcome? Such that the heat transferred during the isothermal segment, AB is isothermal segment, is the same as that transferred during the original process. Original process is what? QIF. So we will be able to find out such an equivalent thermodynamic path. So this is actually a way of simplifying or breaking the actual thermodynamic process into some simple series of adiabatic and isothermal process, which makes our mathematical analysis of the process much simpler. Okay, so we will be taking forth this discussion in the next video. So just see that you try to contemplate on the conclusion, and then it will be quite easy for us to follow the coming videos. Thank you.